I think will tie some stuff together, but also give you a different perspective on things. Very simple device, very simple topic, and one that we can learn a tremendous amount from. It's kind of a neat, I think it's kind of a neat little problem that's both a toy problem, but also a very practical device that's used very widely in industry. So, oh, and then I guess the last thing is, please use me for office hours. And if you are, I've heard reports that some of our first and second years are having a bit of trouble with the distance math courses. And so again, if you need a little bit of help on that, and if I could help on it, please feel free to rattle my cage, and I bet you could also rattle Michael Figg's cage on that, and we can work through that either in small groups or one-on-one. I'm totally fine with that. Any questions or comments before I get started? Great. Okay. So I'm going to build on our analysis of signals with systems. And today I'm going to focus on, for the signal, I'm going to focus on sinusoids, sines, cosines, complex exponentials. And I have a very simple system to talk about today, and it'll get harder and more general, but it's the simplest. It's one of the simplest things we can think about. And the important piece of this system here is that it celebrates the role of phase. Okay, so phase is a very, very important piece of how a sinusoid might interact with the system. And yesterday or Monday, I believe, we started to talk about filters and filtering action. And so this particular system is a type of filter, but it also has other uses as well. In fact, I've studied it more from a different use, and I'll talk about that. But it's a simple filter. It's also, interestingly enough, a modulator. And so we're going to make a connection between modulators and filters that you should be careful of, because this is one example, but there aren't a lot of other examples. But so in a nutshell, this Wednesday lecture is going to revisit a lot of the things that we've talked about. Sinusoids, filters and modulators. And the new thing we're going to look at, or the thing we've always looked at, but the new thing we're going to focus on, is the role of phase in this problem. So the device that I'm going to talk about, and I'm not going to name it, because if I name it, it's a bunch of people's names that are going to scare you off. So I'm just going to draw it. And I'll tell you what I'm drawing. So what I have is a circuit path. What I have is a circuit path here. The signal splits into two. It goes down these two paths. It comes back together, and it combines back together and goes out this way. And the signal that I'm going to put into this is a cosine of omega t. And so what'll come out of this guy here will be a cosine of omega t, and I'm going to drop a phase, and a cosine of omega t plus a delta, a phase. And so what I'm saying is that the path on the top might be a little bit shorter than the path on the bottom. And so when those two signals come out together, they potentially come out with some sort of a phase shift between them. So y of t, the output, will equal cosine omega t plus cosine of omega t plus some phase shift. And for every instance of omega t, delta can be either 0, it can be pi, or it can be somewhere in between. And if this is 0, then the two cosines add in phase. And if it's pi, cosines are out of phase. So that would be minus, this guy would be, the cosine would either be a +1 or a -1. Matthew, make sure that I have that right, that this value of cosine of pi right. Make sure that I have that's pi and not pi over 2. Yes, Zach.
So right below the 0 that you just wrote in red, does that say cosines add to phase? Is that what that says?
They add together.
Together. Thank you.
So we get a in this case, I get a 1 plus a 1, so that's a 2, or in this case, I get a 1 and a -1, and I get a 0. Yes, Zach? Okay, scared you off. Sorry, Zach. So that's what I mean. Is I can either get something out of this filter, or I can get nothing out of this filter, or I can get somewhere in between, depending on the delta. Okay, and so what this shows is the incredible importance of phase. So phase delta is everything in this filter, determining what comes through. Its phase determines all or nothing, or somewhere in between. Okay. Now, the reason I'm saying this is because, generally speaking, when we look at filters, we always think about the magnitude response. And it's often useful and frankly speaking, equivalent to consider the phase response of the filter. So as we do more and more work with filters, as you do more and more work with filters, you're going to see in class an emphasis on finding out what's going on with the amplitude of each of the frequencies. Now, h of omega, I'm going to remind you, is what we call the transfer function. It transfers the signal from the input to the output. It's usually the output divided by the input. And those are usually in the frequency. So, or actually it's always the frequency. But what I'm saying is we can also understand the operation of filters if we look at the phase response. And this particular system shows the entire operation is governed by phase. And so it's so straightforward to think about this not from an amplitude response, but from what's going on with the phase of the signals on the input to the output. So now what I'm going to do is I'm going to talk to you a little bit about what this device is. And that'll give us the physical realization and some of the applications of the filter. So this structure is a very, very, very widely used component in photonics, particularly in optical communications. And so in that system, what we have, the signal paths here are waveguides in a substrate. And just to be definite, what's usually used is a fancy sounding substrate called lithium niobate. It's a crystal. So it's made up of lithium atoms, nitrogen oxide, and so on. I think it's lithium NiO3 maybe. I got to double check that, but lithium niobate. And so what we do is we add a little bit of material into a certain channel, and that raises the index of refraction and we do that by doping. Now, one of the things we're going to get to when was it? Was it next Friday? Yeah, I believe next Friday. There's a video and an article on semiconductor processing, and so a little bit of this is a sort of a prelude to how we actually make chips, both in silicon, in different types of and different other crystals. And in this case, what I'm talking about is making it in a crystal called lithium niobate. I'm stuck. Oh dear. Huh. This hasn't happened before. Always a time for all right. Let's see how I can get out of this. Save. And sorry about that. I have to, I just decided I'd restart the whole program. All right, let's see if that's any better. Okay, great. So it turns out that if I put a very light doping, a very light salting of material into that waveguide, then the light going down that waveguide gets guided. And so I can then split apart these waveguides exactly the way I've drawn before, and I can bring them back together. And then what I can do is I can put a big old metal pad over that one side. And that means I can apply a voltage. And these particles that are in the waveguide, that are making the waveguide, and in fact, the entire crystal lattice of the lithium niobate responds to that applied voltage. So as I apply a voltage to this crystal structure, the crystal responds to that voltage. And what I mean by that is that voltage provides a force, an electric field that provides a force, and that'll either squeeze the atoms closer together or it'll pull it apart. So let's consider the case that if I squeeze the atoms closer together, then an increase in the voltage is going to increase the index of refraction. And the index of refraction is the speed of the light through the material. So now what I can do is I can speed up or I can slow down the signal depending on an applied voltage. So delta becomes a function of that voltage. And it turns out that I can do that very, very quickly. So I can go from an output equal to 1. I can go between these two states very quickly between a voltage by using a voltage. And the record on this is on the order of 100 gigahertz. So I can modulate an optical signal pretty close to 100 gigahertz on and off, on and off, on and off. And in that, if I can do that, then I can call this a modulator. So this is a photonic modulator that's very, very widely used. It's very, very popular because it's small, it's very, very fast. It's been around for years and years, and so it's very easy to make precisely, although it wasn't at first. An awful lot of material science, a lot of processing, but now all that stuff is known. And so this one simple device has huge applications, in addition to being a really interesting, fun little toy problem that we can consider. Now, let's go back to the mathematics of this and tidy some things up. I'm going to have a signal coming in. It's going to split off into two branches. And this block here, and then it will come out. So I'll have an X in and I'll have a Y out. And this block here is a delay. That block there is a delay. And I can write that delay in a variety of ways. One way I can write it is using Euler's relation. Got to figure out how not to do this. Okay, I can write this delay in a variety of different ways. One way to think about this is if this is an e to the I omega t, then it makes sense to write this delay as e to the I omega delta. I'm sorry, that's wrong. E to the I delta, just a phase shift. And if that's the case, then the output is going to be e to the I omega t plus e to the I omega t times e to the I delta. So I have e to the I omega t times 1 plus e to the I delta. And that's a perfectly good way to look at this. And I'll use that to analyze it. But there's another way of writing this, and this is something that I like to use, and you'll see in later courses. You can also write that as a z to the minus 1. And z to the minus 1 is preferred when you're thinking in terms of discrete time signals. And z to the minus 1 actually plays the role of an omega. Z plays the role of an omega for discrete time signals. But this is perfectly good to start with. As I go forward, I may switch back and forth between those two, and I apologize for that. But that's just anyway. So with this as an input and this as an output, I'll remind you that the transfer function will equal the output over the input. You'll notice that e to the I omega t cancels. And I have a 1 plus e to the I delta. Quick review of Euler's relationship. So I have a real part and I have an imaginary part. There's the real part, and this is the imaginary part. And I just noticed something. I did something that could drive you guys crazy. I'm writing everything in terms of I. I apologize for that. We've always used j as the square root of -1. So I've slipped back into my old bad habits of using I instead of j. It makes absolutely no difference. Sorry about that. So I have the real part of the imaginary part. And so what I'll look at is the amplitude. So squaring the real part and squaring the imaginary part and putting them together gives me this. Does anyone know what that equals?
1.
Very, very good. And so I have 2 plus 2 times 2, I'm sorry, 2 plus 2 cosine delta. So if I plot this between 0, 2 pi, and pi, I get a graph that looks like this. It's curved, so it has a horribly nonlinear response. But there's a little spot, let's say right around here, where this is as linear as it's going to get. And if I wiggle an input signal here, then my output will be also wiggled. So I've drawn this graph from 0 to 2 pi. And this is also equivalent to a voltage. So if I change the voltage on that pad, I can change the output accordingly. And if I have a very small wiggle here, then I get a reasonably undistorted shape here. But if I go too far back and forth, then I'm going to get some serious distortion because of the curve of the cosine function. Okay. So this is a new concept for you to look at a transfer function in terms of an input to an output like that. Just introducing that. It's not, don't get stressed out about it. I won't ask you anything on a test. This is just background information. Fills up your toolbox. It gives you different perspectives on what we've been doing. It's just kind of fun to start stitching stuff together. Now, what I'd like to do is I'd like to generalize on this signal flow diagram. I'd like to generalize on this signal flow diagram. And what I do here is I split my signals. Oops. Can you see me now? Yeah, you should be able to. Sorry. This filter does three things. It takes a signal and splits it. It delays a signal. Four things. It puts it back together. And the fourth thing it did that we didn't talk about was we could also have changed the ratio of this guy to this guy. In other words, we changed the phase, but we could also change the amplitude. So filters split signals, delay relative, the splits. It could change the amplitude of the splits. And then it combines those together. All filters do these things. So what is a filter? A filter is a device that takes a signal, it splits up the signal, delays one relative to the other, maybe change the amplitudes of that, and then puts it all together again. And here's an example where we split it twice into two components. That's the simplest split. We don't even change the amplitude on one versus the other. And we delay one versus the other before combining. So let's be more complicated. What if I split and change the weights on this? Let's do something even more complicated. There's my delay using that fancy weird notation. Let's split it again and delay it and pick a different weight. And I can keep going. And if I do this, my transfer function as a function of the delays if I do this m times, I'm going to have a summation of delayed signals. Yes, Zach?
Is this similar to a circuit diagram?
This it's one layer above it. It's one layer above it. It's an abstraction. So a circuit diagram would be the realization of this picture. So in other words, there's my signal flow diagram. Oh dear. And there's my realization. This would be closer to a circuit diagram. That would be closer to a circuit diagram. That's an abstraction of what's going on. And that's what I'm doing here. So there are some similarities. And let me show you a little bit. Let me go back and really mess things up for us. Way, way back to the beginning. So the signal flow diagram lives at this information processing level. And then we realize that abstraction with circuits, either made out of electrical components, made out of photonic components, or some digital code that we can move into hardware. Zach, is that okay?
Perhaps, I assume.
There's a lot of questions, and this is all brand new material. This is all brand new material, and this is just an introduction. This is the equivalent of going to a huge party, not knowing everybody, and shaking a lot of hands and walking out remembering maybe 2 names. But
all right,
it's a start.
thank you.
So here's a transfer function, and I've written it as a polynomial. And basically, this is a polynomial in z or in e to the I deltas, e to the I k deltas. Now, there's another way we can do this. There's another signal flow diagram that splits the signals, delays them, weights them. And that's this guy here. Where I take the output I delay the output and I put it back together. What do we call this when I take the output and I bring it back to the beginning? Feedback. Excellent. Excellent. So this is a signal flow diagram. With feedback. Still a filter. It still splits the signal, delays it, weights it, puts it back together. And just like I did before, I don't have to stop with just one stage. I can have many stages. And in this case, I have an h of z. And now I have a feedback denominator. There's my feedback denominator. If I call this feedback, you might almost find it sensible to call this feed forward. And that is absolutely a term of art. And then I can put these guys together. So that I can have both feed forward and feedback. I've got the numerator. I've got the denominator. Put them together. And this is every single filter that's out there. Every single filter that's out there can be put into this kind of a structure. And this is great. This is an incredibly powerful picture to have. It obeys all the tenets of what filters do. Splitting signals, delaying the signals. These are the z to the minus k's. This is the amplitudes, the a's and b's, and then all the plus signs that we have. So this is the general form of any filter that we can possibly come up with. So any filter that we want to build can be designed and represented with this kind of a structure. And we got to there from our very simple toy problem of a very useful optical filter. And I'm almost out of time, and so I'm going to shut up and thank you for joining me on an excursion into a whole bunch of new area. Just a whole new way of thinking about things with many different terms that are included, different notations that are included. But at the end of the day, it's moving from there to there to there to there. Have a great long weekend. I will see you on Monday.